Dr. Fisk here on the use of Newton's second law to arrive at the ideal gas law. Let's look at what we have done before in our course. We have used, for example, Newton's second law, Coulomb's law, and special relativity to derive the laws of electricity and magnetism, the Maxwell equations, and ultimately optics by showing that the electric and magnetic fields satisfy the wave equation. Now we're going to look at Newton's second law and derive the foundations of thermodynamics. To do this, we're going to need the concept of probability. So we're going to look at discrete and continuous probability. Here, a little review. If we have, say, 12 different velocities and n sub 3 represents the number of particles that have the third velocity, by dividing by the total number of particles, we get the probability that we have a particle with the third velocity. So this height is a probability. If we add all the heights, we get 1, which is what we're doing here, and that's consistent with saying that n, the total number, is the sum of the individual numbers for the various numbers of particles that have various velocities. When you go to a continuous probability distribution, it's the area under the curve that must be 1, and if you look at an area such as this one, it gives you the probability that the particle has velocities defined by that region. Well, we have here velocity v on the left edge, which begins the region, and then on the far right we have v plus dv, and all the particle speeds in between. And the height here is the function f of v, so this gives you the area, and that's a neat way to look at a condition of the particles having speeds v and on up to v plus dv. When we look at all the probabilities, this integration must give 1. The area under the curve must be 1. And this is understood here to have the limits of integration to cover all of your velocities. We will also need that the pressure is defined as the force per unit area, and the force is also equal to the change in momentum with respect to time. That's Newton's second law, a form of F equals ma. Now we come to a beautiful pair of diagrams which I saw in a great book written many, many years ago that enables us to derive essentially the ideal gas law. We consider a volume of a slanted cylinder, and that volume is the cross-sectional area times the length. And the way this length is defined, dl, with the time frame dt, dl dt is the velocity of the particle coming in. Say from here, it's going to then hit the floor, dl dt being v, and it's going to bounce off, and we're going to figure out what the pressure is due to the particles coming in with that condition. So the cross-sectional area is delta A times the cosine of theta to get you the cross-sectional area, and then you multiply by the dl, the length. Notice that this angle is complementary to the angle on the other side of the line, and if I draw a little right triangle here, this angle with respect to the x-axis is also complementary to that angle, which is complementary to theta, so that would be theta. And if I take the dA times the cosine of that theta, I get the area that's perpendicular on each side to the sides, and I need that cross-sectional perpendicular area to hit that with the dl. So it's delta A cosine theta dl to get the volume. I also need to change in momentum. When the particle hits the floor and bounces off, notice that it's the y component of the momentum that I'm interested in, because the x component just skims the surface, doesn't really do anything. So I'm coming down here. You know, it's easier probably just to consider coming straight down mv first. Let's do that case. mv, so minus mv, hits the floor, turns around, and goes up plus mv. What's the change in momentum? Well, the final momentum is mv minus the initial, which is the negative mv, minus a minus is a positive, and I get 2mv. So once when you can see that, you can kind of understand easily where this is coming from. The v cosine theta is that y velocity. I'm coming in with v cosine theta gets me the velocity in the y direction, and then the same logic applies, and I get the factor of 2. I'm also going to need the probability that the particle's coming in at the angle theta, and that probability distribution, I'm going to call it g of theta, and I know that if I integrate over all the angles, and all the angles coming in here for these slanted regions start at 0 and 90, pi over 2 has to be 1. And how can I get this? There's a clever way. We think of a cone, and if we have a cone where we have all the possible theta angles, we're going to get 2 pi r sine theta times r d theta for the little ribbon width, and that area, when I divide by the area of the hemisphere, which is 1/2 of 4 pi r squared, because 4 pi r squared is the surface area of a sphere, I then get a nice cancellation, 2's, pi's, r squared, and I get sine theta d theta. Now, this sine theta d theta will give me the probability that the angle of the slant will match the slant that I have here. So I'm really interested in particles coming in on the right-hand side of this slant, and this is a probability function that goes from 0 to 90 that gives me the probability that the particles will come in at that slant, using the trick here of that cone to do the analysis. But I'm interested in the probability of the particles coming in from the upper right quadrant here to hit this and then bounce off with the 2mv cosine theta change of momentum. So now I come to a beautiful line which has much physics in it, and this is theoretical physics at its best. And let's look at this. We have here a partial pressure due to the particle coming in at velocity v. And how many particles are going to come in with that velocity v? Well, I start off with the total number of particles and I divide by the total volume of my cube. So I have some kind of a cube in a region where I have the gas in, total volume v, and I hit it with the volume of this slanted tube, which I have here. So that'll give me the number of particles that are in the slanted tube. But how many are heading toward me? Well, 1/2, because half of this probability distribution, because half come down, half go up. So I need that 1/2 here, and this makes sure that the speeds are v, or between start at v and up to v plus dv. But then we're going to shrink that down. So basically, we have the v condition. But what about the angle condition? Because that would include particles traveling v, going down, straight down, and going down here at a different angle. Well, if I hit that with a sine theta d theta, that gives me the probability that they're coming in at the angle theta. Now I'm all set. And then I have the change in momentum with respect to time, divide by the little patch of area for my pressure, and I have the pressure definition, force. So this is basically here number of particles with the correct condition. And then this is the change in momentum for one particle. And then I divide by the area. So that's very, very nice. You should think about that and perhaps read over the notes, or maybe even listen to this tutorial again to make sure you have mastered where all these pieces come from. This is putting together physics in a very creative way. So the partial pressure from this combination, I now notice that the delta A's cancel. They're gone. And I have dl dt, which I put over here and left everything alone. And then in the next step, I see that I can grab all the angle stuff, cosine squared theta, sine theta, d theta. I can move the constant m over to the far left. The 2's cancel. And the velocity I'll move in front of the function of v, because I'm getting set up to do an integral here. Next step, I notice that dl dt is v, so that'll give me a v squared. And we're ready to do some integration to get the pressure. The pressure would be to integrate over all the velocities. In classical physics, you go from 0 to infinity. Doesn't matter. I'm just going to say, hey, integrate over everything that we got, and we'll get then the average velocity squared, or the average. Like if this is your exam score, this is a probability for each of the exams, then you get the average exam score. Happens to be v squared, so we're getting, with the probabilities of the various v squareds, we're getting the average of v squared. See, so v squared bar means the average of the v squared. See, that's neat. Then here we have an easy integral to do. That's cosine cubed theta over 3 with the minus sign. Let's just check that by taking the derivative going backwards. 3 comes down, cancels the 3, cosine squared theta, and chain rule, derivative of the cosine is negative the sine, minus signs cancel. Now we got it, looks good. And at the limits of integration, fairly easy to work out. At the pi over 2, cosine is 0, so minus 0 at the top limit. At the bottom limit, it is minus a third because of this minus sign, the 3, and the cosine of 0 is 1. Cubed 1 is 1, and this is the subtraction of the various results. Upper limit minus the lower limit, minus signs cancel, and look at what we get. This is amazing. We get P is Nm over the volume, the V squared average, 1/3. And look at that. That's the ideal gas law. We have the pressure and the volume together. Look at that. Boyle's law, if this is a constant. And this tells us that we have great insight as to what is temperature. Temperature is kinetic energy of molecules. Look, the average kinetic energy of the molecules, amazing result. Here you have kinetic energy is the number of particles times the kinetic energy on average of each one. So N times that is the total kinetic energy, and that's related to the temperature. So we get a bonus here. We get insight as to what temperature is. So PV, we have this calculation, and we're going to set that to KT. So we define temperature in the traditional way. And look, we even know how the Boltzmann constant is related to this. This is going to be a very, very nice result because, see, if you look at these two last pieces, n's cancel, bring the 3 over to the KT, divide by the 2, and you get 1/2 mv squared. The kinetic energy, average of the kinetic energy, per molecule, per particle in that, or per atom, in a gas, is 3/2 kT. This is called the equipartition theorem because the physicists like to think of the velocity in 3 dimensions, having an x component, a y component, and a z component, and each of those components, independent components, give 1/2 kT. And since you have 3 dimensions, you have 3/2 kT. And our summary is PV is nRT or PV is nKT. These are your definitions of your various forms of the ideal gas law, the way the chemists like to write it, or the physicists like to write it, as we talked about in an earlier chapter or section. And this is the nice result that the average kinetic energy of the gas per molecule is 3/2 kT. The temperature related to the kinetic energy of the gas.